A 3,250 kilogram car experiences a braking force of 11,500 newtons. If the car initially had a speed of 80 kilometers per hour, what is the braking distance? So I like to start a lot of my problems with sketches, especially when it's relevant to do so. And this seems like a good one where I can maybe like draw a little sketch of this car. So let me, I don't know, it doesn't have to be big or perfect or anything like that. So I'm gonna say, okay, here's maybe this car, something like that, whatever. Okay, hopefully that's good enough for a car. And we're saying that it's traveling. I'm gonna have it travel to the right in my picture. So in that sense, like that may represent the 80 kilometers per hour it starts with, or at some particular moment it is slowing down, right? So at some particular moment, I'm just going to maybe give it a velocity v there in my picture. If it's braking, it means it has an acceleration in the opposite direction. So I'm going to put that in my picture as well and say, okay, this is its acceleration vector in the opposite direction, representing the fact that it is in fact braking. Now, one of the things that the problem didn't say is it didn't assume that this was, it didn't state explicitly that this car is on a horizontal surface, but I think I'm just going to assume that that is the case since I'm not told anything different, and that kind of makes sense. Maybe I should have put that in this problem statement, but anyways, I'm just going to make it so right now. The next thing I think I'm going to turn to is I'm going to draw an FBD, and why am I doing that? Well, we're doing Newton's second law, so it kind of makes sense, but the other clue is I have this acceleration here. I have a velocity. I was given an initial velocity. I'm thinking, since I'm given information like mass and a force, maybe I could calculate what that acceleration is based on a free body diagram and applying Newton's second law, and then I could go into some kinematics to figure out the actual answer to this question. So that's kind of my strategy here. So I'm going to draw a system point for this car, and we can recognize this car definitely has gravity acting on it. It has a normal force acting on it, although I don't know if I'm all that interested in those. And it's going to have a braking force, right? And that's the one that's given to us. That's why I said I'm not sure if I'm interested in those other two, because they really, if it's on a level surface, they just cancel each other out. But there's definitely some kind of, maybe I'll just say F sub B for braking force and recognize that force is that 11,500 newtons. So maybe somewhere over here I can say, okay, F sub B is equal to 11,500 newtons. There it is. Okay, let's do F equals ma. So we're doing Newton's second law. Really, this is the net force. So strictly speaking, I mean, I don't know if in this one if I need to really do it. I mean, you might be able to skip some of the steps I'm going to show, but I'm going to try to show kind of the logic of things. And I would say, strictly speaking, what Newton's second law says is that it's the net force, which means really the sum of all three forces in the free body diagram. So it's definitely like sometimes worth writing all those as a vector equation. But one of the things that we might recognize is, again, these vertical ones, am I really that interested in that? Because I kind of said, you know what, maybe I'm interested in that. Maybe I'm interested in the acceleration. So I've got a vector equation. Maybe I can just look at a component equation. One of the things, you know, I've often just started writing components, but one of the tricks that I learned from an engineer at one point was, that I think is really cool, is if I'm saying, you know what, I'm going to do like horizontal components here, because I'm interested in horizontal acceleration. So I write X with a colon here, and then I'm just going to do those horizontal things. And in that sense, the braking force is clearly there. Although, let's see. If I have my X direction the standard way, shouldn't this be a minus F sub B? Because this is pointing to the left. That's just the way I drew the picture. That's okay. I think I can do that. But I don't need to include gravity or the normal force, because their components in the X direction would be equal to 0 since they're both oriented perfectly vertically. So I'm just going to skip those and then write MA. And I'm just going to write A. And I haven't put any sub X subscripts here this time. I've made it clear I'm doing X components, but the reason I haven't put them is based on my picture. It's pretty clear there is no like X and Y subscript for these things. Acceleration is purely in the X direction. The braking force is purely in the, well, negative X direction, and I've made that explicit here. Actually, one thing I might like to do, depending on what perspective I'm taking on this, because I kind of wrote this as MA, and I'm probably going to, if I plug in a number here, I've got mass, I've got force, I'm going to get like a negative acceleration. So I have to kind of make a choice. Am I going to work explicitly with signs? I'm going to choose to explicitly make this a minus MA over here, recognizing that this is my acceleration. I'm just going to calculate what its magnitude is, but really the direction of acceleration is to the left, which is also the minus direction. So I'm going to kind of follow the same convention I did here for this force and put that minus sign in there. But this tells me those minus signs then can really cancel out. Acceleration is just equal to that braking force divided by mass. Let me make that be a little bit better on the braking force. So that's going to be 11,500 newtons divided by 3,250 kilograms. And it turns out the way the Newton is defined, if you wonder about the units here, the Newton is defined so that if you take a Newton divided by a kilogram, it will give you a unit of acceleration, and that will be in meters per second squared. Moreover, the Newton is actually, I can write this down here since we're still a little bit new on this here. The definition of the Newton, kind of following F equals ma, is that it is a kilogram meter per second squared. So when you divide off a kilogram, you're going to get some number in meters per second squared. And I get like 3.53846, etc. Let's see, it looks like we're going for maybe at least 3 sig figs here, but this is an intermediate result, so I think I might want to write down a couple more. I mean, let's see, maybe 2 more. So 385 should be sufficient if you're following along with your calculator, so we don't avoid too much round off error, maybe a little, but hopefully not too much. Anyway, that gives me the acceleration, but now to answer the actual question here, I might want to recognize, okay, we're talking about a situation where there's an initial speed, final speed is 0, and it's braking. I think this kind of fits the fourth kinematic formula. There's no time involved. In other words, like I'm just going to write this down. Fourth kinematic formula again. But I might want to recognize, I think I want to change something a little bit here, because in this situation, the object is slowing down, so I'm going to make the acceleration again explicitly negative here. So I'm going to make that a minus sign, indicating that A is, again, using explicit signs, negative. And the final velocity is equal to 0. So that tells you that if I add this 2a delta x to both sides of the equal sign, then maybe move some things around or switch sides on some stuff, I'd wind up getting with v naught squared is equal to 2a delta x, and that would mean that delta x is equal to v naught squared over 2a. In other words, I've divided both sides by 2a. Notice that I've really left, like I could have put in numbers already here, and that's fine if you want to do that, but I have limited space on this little space that I have here to write, so I didn't want to do that because it winds up occupying a lot more space, and it's fine if that makes you more comfortable if you want to do that. Anyways, I think what we should put in now is like this v naught here really represents the 80 kilometers per hour. In that sense, maybe somewhere, I'll add it to the top here. That v naught, the initial speed given to us, was really 80 kilometers per hour. But something I might like to do with that is convert that into meters per second, right? So this, this should be equal to, like, let's see, if you do 80 kilometers per hour, if I left enough space up here for this, but you'd probably multiply by like 1,000 meters per kilometer. And then in every hour, there would be, make that an hour there. There would be 3,600 seconds. And so I get a number for that. I haven't actually computed that number separately here. So I think what I'm just going to do is I'm going to put in the V naught here. I'm just going to put in 80 times 1,000 divided by 3,600, reflecting those conversion factors. And that's definitely in meters per second squared. And that all of that divided by 2 times the 3.5385 meters per second squared. And then I'm going to put that into my calculator, and rounding it off, I wind up getting 69.8. We're calculating a distance, so I'd expect the unit on this to be in meters. Can we check if that makes sense? It looks like it does, because this square would square that meters there. One would get canceled out with this meter down there. There'd also be a second squared or an over second squared. That would get canceled by the over second squared there, leaving us with meters. So I think I'm ready to go ahead and check my answer now and see. Looks like everything worked.